BAC 101, the science behind the world's only complete DPF cleaning solution. Diesel particulate filters, DPFs, are an engineering necessity. Mandated by emissions legislation and fitted to virtually every modern diesel engine, they capture the harmful particulate matter produced during combustion and prevent it from being released into the atmosphere. In principle, the system works well. In practice, however, the management of what accumulates inside a DPF has become one of the most significant and costly challenges facing the trucking industry today. To understand why, it is essential to understand what actually builds up inside a DPF, and why not all of those substances are equal when it comes to removal. When a DPF traps particulate matter, it collects a mixture of substances: soot, carbon deposits, unburned hydrocarbons, oil residues, and, most critically, ash. Soot and carbon are, by their nature, combustible. This is precisely why the DPF's built-in regeneration process works as well as it does. By raising exhaust temperatures to somewhere in the region of 550 to 600 degrees Celsius, the engine can burn off accumulated soot and carbon in a process known as active regeneration. The filter is, in effect, self-cleaning, at least in terms of those particular contaminants. Ash is an entirely different matter. Ash within a DPF is the incombustible residue left behind after regeneration. It originates primarily from the metallic additives present in engine lubricating oil. Compounds such as calcium, magnesium, zinc, and phosphorus, which enter the combustion chamber through normal engine operation and pass into the exhaust stream. Unlike soot and carbon, ash cannot be burned away. No matter how many times a DPF undergoes regeneration, the ash remains. It does not combust, it does not break down under heat, and it does not dissipate. It simply accumulates, layer by layer, compaction by compaction, embedded deep within the filter substrate. This is the core problem that the industry has, for decades, largely failed to address. Ash is extraordinarily difficult to remove from a DPF without first physically removing the filter from the vehicle and subjecting it to a specialist cleaning process in a dedicated tank. The geometry of a DPF, a honeycomb of narrow, parallel channels, means that ash, once compacted into the substrate, has virtually no path out. It cannot be blown out, it cannot be burned out, and until now, it could not be chemically extracted without disassembly. The consequences of this accumulating ash are profound, persistent, and, for the trucking industry, enormously expensive. For a long-haul truck completing approximately 120,000 miles per year, the DPF is under near constant stress. The engine's attempt to burn off accumulated soot are a normal and expected part of operation. When the filter is clean and functioning optimally, regenerations are relatively infrequent and efficient. But as ash builds up within the filter, the picture changes dramatically. Ash narrows the available channel volume within the DPF. The filter begins to backpressure the exhaust system, forcing the engine to work harder to expel gases. Soot, which would previously have been captured in a filter with adequate capacity, now accumulates more rapidly because there is simply less space available. The engine's engine control unit, ECU, detects the rising differential pressure across the filter and triggers regeneration cycles more frequently. Each regeneration demands that the engine inject additional fuel to raise exhaust temperatures to the levels required for combustion of the soot deposits. Fuel that contributes nothing to forward motion and everything to operating cost. This is not a marginal inefficiency. For a truck covering 120,000 miles annually, the fuel consumed purely by DPF regeneration, above and beyond what would be required if the filter were clean, can account for as much as 4.6% of total fuel usage. On a vehicle that might consume 30,000 to 35,000 liters of diesel in a year, that figure represents thousands of liters of fuel burned entirely in service of a filter that is increasingly failing at its primary function: simply because the ash inside it was never properly removed. Multiply this across a fleet of dozens or hundreds of vehicles, and the scale of the problem becomes clear. This is not an inconvenience. It is a structural cost burden embedded in the operation of almost every diesel truck on the road, driven almost entirely by the inability to effectively remove ash from the DPF without taking the vehicle off the road for a full filter service. Beyond the direct fuel cost, there is the compounding damage to consider. Running at high temperatures, more frequently than the system was designed for, place enormous thermal stress on the DPF substrate itself. Over time, this accelerates wear, increases the risk of filter cracking, and shortens the operational lifespan of what is an extremely expensive component. Replacement DPFs for heavy commercial vehicles routinely run into thousands of euros, pounds, or dollars. And when labor costs and vehicle downtime are factored in, an unmanaged ash problem can quickly become a catastrophic operational expense. The DPF cleaning aftermarket is not short of products. Additives, sprays, flushes, and on-vehicle cleaning solutions have existed for years. They are widely sold, widely used, and to varying degrees, they do work. The question is not whether they work, but what they work on. The honest answer is they work on soot and carbon, because those are the easy targets. Soot and carbon deposits, while challenging to remove mechanically, are relatively amenable to chemical dissolution. A range of fairly basic chemical compounds, alkaline cleaners, detergents, mild solvents, can break down the carbon matrix within a DPF and allow it to be flushed or purged from the filter. For a vehicle whose primary issue is soot loading, these products can produce a measurable improvement in filter performance, reduce back pressure, and restore some degree of regeneration efficiency. This is why these products have always attracted customers. They deliver a result that is visible and real. Back pressure drops, warning lights extinguish, regeneration intervals lengthen. The truck feels better. The operator is satisfied. But the ash is still there. It was always still there. Every existing DPF cleaning product on the market, before the development of BAC 101, left the ash behind, because none of them were formulated to address it. The chemistry simply wasn't there. Ash is not soluble in the kinds of compounds used to dissolve carbon. It cannot be dislodged by the same mechanisms. And so it accumulated, untouched, behind every cleaning cycle, continuing to restrict the filter, continuing to drive up regeneration frequency, continuing to drain fuel economy, quietly, invisibly, persistently. When a DPF cleaning product leaves ash in the filter, the cleaning process has not been completed. This is not a technicality. The ash is the primary long-term contaminant. It is the substance responsible for the irreversible reduction in filter capacity. Removing the soot and carbon without removing the ash is, in the most practical sense, an incomplete service, one that gives the impression of a solution, whilst leaving the underlying problem entirely unaddressed. A DPF can only be considered genuinely clean when all four categories of contaminant have been removed: carbon, soot, oil deposits, and ash. Anything less is, at best, a temporary measure. When our team set out to develop what would become BAC 101, the goal was unambiguous. We were not going to build another product that cleaned what was easy to clean and ignored what was hard. We wanted a genuine solution, one that addressed every contaminant category, including ash, whilst the filter remained attached to the vehicle. We understood at the outset that this was a significant scientific challenge. The chemistry of ash removal from a confined, geometrically complex substrate is genuinely difficult. Ash cannot simply be dissolved, because the compounds that form it are highly stable inorganic residues. Aggressive mineral acids can attack some ash components, but they are equally aggressive towards the DPF substrate itself, which is typically constructed from cordierite or silicon carbide, materials that cannot withstand the kind of chemical environment that would be needed for brute force ash dissolution. The path to a solution, it became clear, did not lie in trying to dissolve the ash directly. It lay in changing what the ash does inside the filter. Before we could find that path, however, we faced a more fundamental challenge: the sheer number of possible chemical combinations to consider. The universe of compounds, concentrations, sequences, and formulations that might be relevant to this problem runs into the many millions. Testing them one by one in a laboratory would have taken generations. We needed a smarter approach. We turned to artificial intelligence. By developing and deploying a bespoke AI model trained to evaluate chemical compound interactions against the specific conditions and material constraints of a DPF cleaning scenario, we were able to reduce the field from many millions of possible combinations to a short list of only a few hundred. The AI did not find the answer, no AI model does, in isolation, but it compressed years of theoretical elimination into a fraction of the time, and it identified candidate combinations that human intuition alone might never have reached. From that short list of a few hundred, we moved into the laboratory. Systematic testing, reformulation, and evaluation over an extended development period further narrowed the field. Some combinations that looked promising in theory failed in practice. Others performed well in isolation, but poorly in sequence. Gradually, the field narrowed, until we arrived at the two-part formulation that became BAC 101. The fundamental insight that makes BAC 101 possible is a reframing of the ash removal problem. The question is not, how do we dissolve the ash, because that path leads either to chemical failure or substrate damage. The question is, how do we move the ash? Ash that is bound to other materials, particularly carbon, can be mobilized in ways that free ash cannot. The BAC 101 process leverages this principle across two precisely sequenced chemical stages. Part 1 is introduced into the DPF filter in its functioning position on the vehicle. Its primary action is to dissolve the soot and carbon deposits within the filter, converting them from solid deposits into a liquid phase that can be drained or purged. This is, in itself, a more thorough version of what existing cleaning products achieve. But Part 1 does something that no other on-vehicle product does. Whilst the carbon is being dissolved, a specific portion of the carbon compound is simultaneously directed to act as a binding agent for the ash particles. The result is not simply dissolved carbon, it is a slurry in which the ash, previously locked into the substrate, has been drawn into a chemical association with the carbon matrix. The ash, which could not be moved on its own, can now be moved as part of this combined material. Part 2 builds on this foundation. Its role is threefold. First, it provides a secondary binding action that combines any remaining dispersed soot, carbon, and ash into a manageable, removable form. Second, and this addresses the fourth category of contaminant that other products have never touched, it breaks down the oil deposits within the filter. Oil residue is a persistent contaminant that coats the DPF substrate, reduces filtration efficiency, and contributes to the kind of irregular, difficult to predict pressure behavior that makes filter management challenging. Part 2's formulation includes compounds specifically selected for their ability to break down these hydrocarbon deposits without damaging the substrate or interfering with the binding work already completed by Part 1. The combined effect of the two-part process is a complete cleaning cycle in the truest sense. All four contaminant categories, carbon, soot, oil, and ash, are addressed, mobilized, and removed. The filter that results is not a filter that has had its most accessible contaminants cleaned away, whilst the harder problem festers inside. It is a genuinely clean filter, with restored channel volume, reduced back pressure, and the capacity to function as it was designed to function. This is the only process currently available that can achieve this result without removing the filter from the vehicle. 4 years in development, 2 years of real-world proof. BAC 101 did not emerge quickly, and it was not released before it was ready. From the initial AI-assisted compound screening to the delivery of the final formulation, the development of BAC 101 took 4 years in total. The first 2 years were devoted to the scientific work, the AI modeling, the laboratory testing, the iterative refinement of the two-part chemistry, and the rigorous evaluation of safety, efficacy, and substrate compatibility. Producing a formulation that works is not enough. It must work reliably, consistently, and without causing harm to the filter itself or to the vehicle system. The final 2 years were spent in real-world testing. Laboratory conditions, however carefully constructed, are not the same as the varied, demanding, unpredictable environment of a working diesel vehicle. Filters from different vehicle types, with different degrees of ash accumulation and different contamination histories, were treated with the BAC 101 process. The results were measured not just immediately after treatment, but over extended operating periods, monitoring regeneration frequency, fuel consumption, back pressure behavior, and filter longevity. The data confirmed what the chemistry had predicted. BAC 101 delivers a measurable, sustained improvement in DPF performance, not because it partially addresses the problem, but because it is the first product formulated to address all of it. The standard has changed. For too long, the DPF cleaning market has operated on a convenient compromise. Target what is easy to remove, claim a result, and move on, leaving the ash and the real problem exactly where it was. BAC 101 was developed because that compromise was never acceptable to us. The trucking industry loses enormous sums to unnecessary regeneration fuel every year. Fleet operators invest in DPF cleaning and see incomplete results. The ash accumulates, the filter degrades, and the cycle repeats at enormous and entirely avoidable cost. BAC 101 is the product that changes this. 4 years in development, 2 years of real-world validation. The world's only complete on-vehicle DPF cleaning process. The filter is clean when everything is removed. BAC 101 removes everything. BAC 101, developed for the industry, built for the future.